Thanks for asking me to talk at this conference and for having us, everybody here in Durban. And so I'll just say a few things, and I'll try to. I know some of you have heard this or version of this talk before, but I'll let you know when there is some new stuff that maybe you can pay more attention to. So I'll be talking about a project that we've been working recently with my student Hector, who's there in the audience, plus some other people that I'll mention in due time. So just also to place where I'm based geographically. So Pretoria is here, very close to Johannesburg, but it's not the same place. And we were talking the other day about the Cherry Blossom Festival. Well, in Pretoria we don't have cherry blossoms, but we have the jacaranda trees. So, okay, it's hard to see here, but the whole city becomes very purple. And you were thinking perhaps one day there should be a jacaranda workshop as well. Since now there's going to be a cherry blossom workshop. Okay, so, and this is just a view of the campus. This is not where I work.
What is the front page building?
The front page building is the administration building, actually. Obviously, they have one of the nicest ones. And, but the interesting thing is they have this, they focus a lot on indigenous sort of plants and stuff, so they have this huge aloe kind of exhibition just in front of the building. You cannot, again, see it very well, but it's quite spectacular when it's in the blue. Okay. So let's go to physics. So what I want to do in this talk, and please stop me if I'm going too fast on some of these things, is to discuss the symmetries and integrability of the marginal deformations of the n equals 4 four-dimensional Zoubos-Mills theory, and explain why I think it's a nice perspective to take to generalize the study of these symmetries of these quantum field theories from Lie algebras to Hopf algebras in a particular way that I will explain. And having discussed these Hopf algebras, then I'll move on to introduce something that I'm going to call a twist. Basically, it's going to be used to create a star product, and as an application of sort of these ideas, I'll show that for a specific deformation, I can use the star product in the dual supergravity perspective to actually construct the dual supergravity background of that marginal deformed theory. It's not going to be a totally new example because it will turn out to be equivalent to theories that we already know, but it paves the way forward, I believe, to actually generalizing this and using it as a proper solution generating technique in supergravity. Okay, so I'm going to go quickly through this, this slide. So obviously we all know, and we've been hearing also in the past few days, about n equals 4 Zoubos-Mills, which plays this super fundamental role in the study of gauge and string theory. And you can define it as the unique four-dimensional gauge theory with the maximum amount of supersymmetry. And it has all these very interesting properties, perturbative finiteness, non-perturbative finiteness. So this was something which was sort of understood in the maybe late 70s, early 80s, and many approaches, including Mandelstam, I guess, played some role in getting this understood. Then there's the non-perturbative finiteness story, which one can also see. Well, I guess the final discussion of this, I guess you can talk about normalization theorems and stuff like that, which was developed in the 80s. There's the DCFT correspondence. There's planar integrability. So basically, it is believed that by now the spectral problem of the n equals 4 theory is completely solved, so that you can, at least in the regime of not too heavy operators, you can write down the equations that give you the full spectrum of the theory, and it also plays a role in planar amplitudes and so on. So the question one could ask is this the unique theory that has all these nice features? Are there perhaps theories, and the answer is yes, most likely, but are there theories which share some of these features, but maybe not all of them? And all this knowledge that, especially since the work of integrability, so the Minahan's Rainbow paper in 2002, there has been a huge explosion in the study of integrability in this theory. Can some of that knowledge help to understand more realistic theory, which maybe don't have all of these features?
Costas.
Yes.
So you don't list S duality as an interesting property of n equals 4?
Yes, yes, definitely. I should have listed it. Yes, yeah, I guess it should go there probably. I'm not sure exactly. Probably here, Montanal Olive. Yeah, so definitely I should list it. Okay. Although it's kind of okay. Once you talk about ADCFT, maybe it's included in the type to be story. Okay, so what we're going to do is look for theories which are as close as possible to the N=4 theory. And I'll focus on situations that preserve conformal invariance. So these are going to be marginal deformations, and they'll also preserve supersymmetry. So the maximum I can preserve while deforming the N=4 theory, which is N=1. So if I were to write this in N=1 superspace, the notation is like this. I'm not going to go through it. If you don't know what superspace notation is, you're not really going to need it very much to understand the symmetries that I'm going to discuss. All you need to know is that you can write the Lagrangian in terms of these integrals, these chiral and anti-chiral integrals in this superspace, where the superpotential depends on these chiral superfields, which are particular combinations of the fundamental fields. So the N=4 theory contains 6 scalar fields, which are the adjoint representation of the gauge group. Now I'm organizing them in terms of 3 complex scalar fields, and then that creates 3 complex chiral superfields, and the superpotential looks like this. Now, and of course this is, we know that this theory is at least classically conformally invariant because this is cubic, and the rules of superspace tell you that if you go to the potential, you're going to get a quartic potential, and that is the correct dimension of a potential to get classical conformal invariant. Basically, essentially, this coupling has to be scalar. I mean, it has to not depend on the dimension. Okay, so now if you want to deform this, suppose you want to take this and do a deformation, it turns out that the most general, classically marginal deformation is when you deform the superpotential by a tensor HIJK, which is symmetric. You could imagine something a bit more general, but it turns out that by Fielder definitions you can get rid of the cases with mixed symmetry, and you can focus on a symmetric tensor HIJK. And the question now is which of these deformations are exactly marginal. So it's not only that you deform and it's marginal to first order or whatever, you want it to be exactly marginal. And there have been perturbative approaches, but I guess the focus, I mean the main sort of understanding of this came with the work of Liam Strassler in '95, using the NSVZ beta function, from which basically the study, okay, I'm not going to go through this, this argument, but what the NSVZ beta function did, or what the argument Liam Strassler used, is that if you assume that the anomalous dimensions of the 3 scalar fields are equal, and then you ask for the beta function to vanish, then what you find is this superpotential, where there's 2 differences from the N=4 case. First of all, this commutator has been deformed to a Q commutator, so there's a Q here, which in the case of N=4, this would just be 1. And also you add this cubic term. Now the reason for this particular form is that the assumption that I just mentioned, that the anomalous dimensions are equal. Okay, so that essentially introduces a Z3 symmetry that you need to have between the scalar fields. I'll discuss it a bit later. And that's what makes this all the possibility. So you can think of other cubic stuff, but they won't have that Z3 symmetry. So now this, of course, this is not the end. We have also another coupling kappa, and of course there's also the gauge coupling, which is in a different part of the Lagrangian of the theory, the Kähler part. So we have 4 couplings, and what one can argue is that this is finite if a given function of these 4 couplings vanishes. Now this function is not a trivial function. We don't actually know, basically this is the function defining our conformal manifold. We don't actually know that function. You can calculate it perturbatively. So one of the calculations, it was in work by Razamat and Haroni, for instance, and they found something like this to one loop. And you can see that apart from the couplings G and kappa and Q and H, you also have the rank of the gauge group up here. Okay? So there's a different story between the planar limit and the non-planar limit, or beyond the planar limit. If you're in the planar limit, things simplify, but it's still not a known function. Okay. This is not going to, I'm not going to be worried about the particulars of this function in this talk, but I'm just pointing out that it's an interesting question. What is the conformal manifold of the marginal deformations of N=4? Okay, so how do these least rational theories compare with n equals 4 theory? Well, they're supposed to be fully conformally invariant, non-perturbative. Do we know there are these CFT duals? Yes, for n equals 4. For least rational, we know it for complex beta. And I'll discuss a few aspects of this Looney Mandelstam solution later. But essentially what they do is they use T-duality to take the ADS5 versus 5 dual of n equals 4. They apply T-duality along some U1 direction, then they shift along some other U1 direction, and they apply T-duality back. And that actually gives them the deformed theory. And then they do this SL2R transformation, so basically the kind of strong-weak transformation to actually get the complex. So that was the real, because they can only shift by a real angle, and that was this real beta. But now after SL2R you can get the full complex solution. And planar integrability has been studied, and obviously for n equals 4 we believe that's there. For the least rational theories, it's essentially, and I'll qualify that basically thing there later, it's only there for real beta. So if you want to write down the spin chain that you get in the complex beta case, and you want to study planar integrability, what you find is that it's not there. Something breaks this integrability. And that's somehow my entry point into this kind of discussion. One would like to understand from a symmetry perspective, why, for instance, is real and complex beta so different? Why does real beta preserve integrability, complex beta seems not to preserve? So let's take a closer look at the symmetries of these theories. Now, obviously, for n equals 4, we have this full superconformal group. I'm going to focus on, I'm not changing the conformal part, so I'm only focusing on this SU4, which you can also think of as an SO6. But actually, in n equals 1 superspace, the SU4 splits into an SU3 times U1, and this U1 we're not, again, changing, we're not tampering with this U1 because we want to preserve n equals 1 supersymmetry. Now, there are other more general deformations called gamma I deformations, where you also change, you also break that U1, but I'm not going to deal with that. Okay, so why does this superpotential, which is the same one that we wrote before, you can write it in two different ways. So this is one way, the commutator, and this is also, you can rewrite this in terms of the Levi-Civita tensor. Why is this SU3 symmetric? Obviously, because if you do an SU3 transformation, so change these phi's, or here these phi's to uij times phi j, then since epsilon is this invariant tensor of SU3, this gives you the determinant, and this is 1. Right? So this is an SU3 invariant superpotential. Now, what if we go to the least rational theory? What's the story there? You have, this is the least rational superpotential, and generically, apart from this U1 R symmetry, these are the only symmetries you see. So this is the important Z3, the one that guarantees that the anomalous dimensions are equal, which takes phi 1 to phi 2, phi 2 to phi 3, and so on. And there's another Z3, which where omega is a square root of cubic root of unity. Now there's actually a third Z3, which acts within the U1. So that's kind of roughly one way of seeing how it acts. This one, if you put them all together, these three Z3s, they form a dihedral group, which has been studied by Haroni and friends, and they call it delta 27. This is not going to be important for me because, again, I'm not dealing with this U1R Z3. Okay, so that's basically all. Now, if you take beta real, actually, yeah, in principle for any beta, but definitely for a real beta, you see, so this term is not there, and now you can start doing U1 rotations here. So there's, now you'll see the form a bit later, but you can actually rotate not only in Z3s, but actually a full U1 rotation. So that's one of the big differences between, say, the real beta case and the generic case, that you have this enhanced symmetry because you have some U1s. But this is everything. Okay, now comes the part where I diverge perhaps from the literature. So far, this is some work that we did with Theresia Monson back in 2008. And there we claim that actually, even though it's kind of obvious that this global SU3 symmetry is broken if you go to the least rational case, we claim it's actually not broken. It's actually deformed if you think in the Hopf algebraic sense. So the claim is that if you take the phi's in this superpotential, so take these phi's and transform them under this transformation here, where T is a 3 by 3 matrix, but it's not an SU3 3 by 3 matrix because these T's now are taken not to be C numbers. They are taken to actually be, you can think of them as operators, and they do not commute. These are the commutation relations that they have. So now I'm not talking about, of course, the matrix multiplication, which is always non-commutative. I'm talking about the elements of the matrix, which also become non-commutative. So the product between elements of the matrix is non-commutative. And if you decode what is called here, you could find, for instance, that, say, T11 times T12 equals Q times T12 times T11. So if you take these elements of the matrix, they're actually non-commutative. I'll discuss how we got these formulas a bit later. So what is actually happening here is that we've moved into the domain of bialgebras and eventually Hopf algebras. So I'm not going to focus on this slide very much, but remember that an algebra, one of the defining features of an algebra is that it has a product. So some way to take two elements and give you one element of the algebra. Okay, for a Lie algebra that would be, for instance, the commutator, the Lie bracket. But for a coalgebra, you also have, apart from the product, you also, well actually, instead of a product, you actually have a coproduct, which is an element that takes you from one element, it's an operation that takes you one element to two elements. And I'll give an example in the next coming slides. So what we're claiming now is that we have a bialgebra, which is both an algebra and a coalgebra, and actually a particular kind of bialgebra called a Hopf algebra, which satisfies some extra conditions, including the presence of something like an inverse called the antipode. So how does this construction work? Okay, let me just remind you where you've seen coproducts before. So for Lie algebra, they also have a coproduct. So Lie algebras are also Hopf algebras, but their coproduct is kind of trivial. So if you take an element of the algebra and you apply the coproduct, you get something like this. So that's two copies of the algebra. But the way it works is kind of very simple, and this is actually what we apply all the time in quantum mechanics. Suppose we have a product of two states, and we want to act with the angular momentum operator, or the spin operator S, the vector S. Well, of course, S does not know how to act on two copies of an algebra. It's an SU2 element, for instance, so it only knows how to act on the representation space of SU2. Here we have two copies of that. So what do we do? Well, we apply coproduct, and we use that definition of the coproduct, which basically tells us it applies first to the one, and trivially to the other one, and the other way around. So it's something which is, of course, very natural and makes perfect physical sense, is what appears in quantum mechanics. So basically, this coproduct, in this case, is commutative. Tau is the operation that exchanges the two copies of the action of the coproduct, so these ones, and obviously that gives you the same thing. Now, so one way to think, a nice way to think of Hopf algebras is when you take a Lie algebra like this, but you make its coproduct non-commutative. For instance, if I had a Q here in front of the second term, and now apply this, exchange, I would not get the same thing. So then I would have a non-commutative coproduct, and now this is not a Lie algebra anymore. Okay, that was my crash introduction to Hopf algebras. So in practice, one way to construct them is using these RTT relations of diversity and Tartagnan, where you start with an object R, which belongs to two copies of the algebra, and since each copy of the algebra is a matrix, it has two indices, Tij. This thing has four indices because it's in two copies, and it takes two copies AB to two copies Ik. So that's called an R matrix. And if you define relations like these, where T's are now the generators, you get those complicated commutation relations I had a few slides ago, with a given R matrix, which I'll write in the coming slides. So there are many things that one can say about this, but one important aspect of this R matrix is that it satisfies this quantum Ye-Baxter equation. And the reason for this is, well, you see the problem with defining something like that. So take some arbitrary matrix here and define some commutation relations between generators. That's perfectly fine at the quadratic level. But now what happens at the cubic level? Suppose you want now to have these relations, but you basically want to multiply things at the cubic level, but also assume associativity. The problem is that these things might not be compatible. You might actually get at the cubic level relations that eventually lead you to actually kill some of your generators. You might have to set things to 0 in order to satisfy associativity. If you start from some arbitrary quadratic commutation relation, that's kind of a general problem. But in the case, that's what Deverstein-Tartezan showed, that if the Yang-Baxter equation is satisfied, then in the algebra, this doesn't happen. So all the higher order cubic quartic relations, they follow from the quadratic ones. So everything is consistent, and the algebra is not too trivial. And then you can proceed. So this is the R matrix that we're dealing with. Actually, we start off with one loop Hamiltonian. Royman in an old paper showed how you can just directly read off the one loop Hamiltonian from the Lagrangian of the theory. Okay, so this would be the spin chain Hamiltonian acting in the SU3 sector of three scalars, phi 1, phi 2, phi 3. But you can just read it off directly. You don't have to construct the spin chain first. And it looks somehow like this. So when this is acting, now the reason this is 9 by 9 is because it's acting on the space of three scalar fields. So you can think of this as acting on 1, 1, 1, 2, because it's two scalar fields that it's acting on. So it's 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, and so on. That's how we construct our bases. So this is a 9 by 9 matrix. And the R matrix is very simply related to this one by basically 1 minus the Hamiltonian, and then you swap two of the indices, and then that's the standard definition of what's the R matrix associated with. So this is the beginning in the integrability. If you're interested in integrability, this is kind of the beginning of the discussion of how you can construct algebraic Bethe-Ansatz and many things. You might want to use some of these the Yang-Baxter equation that this satisfies. But the thing is, for our case, for the generally started deformation, this matrix does not satisfy the Yang-Baxter equation. Which of course makes sense, because Yang-Baxter equations is more or less very strongly connected to integrability, and we know that these theories in general are not integrable. So it would be a bit of a surprise if it actually satisfied the Yang-Baxter. But still, what we showed in this paper with Monson is that you can still get a Hopf algebra in the general case. So the Hopf algebra is still there, and that was, in a way, very surprising, because what it depended on is that there is some concept of a quantum determinant, which is a cubic element of the algebra, and when you start talking about cubic elements, you might run into the problem that I mentioned, that because of the Yang-Baxter equation not being satisfied, these might trivialize. That did not happen in this case. The precise combination that was the quantum determinant was perfectly consistent, and it was central. Central means it commutes with all the other elements of the algebra, which means you can set it to be a C number. And in particular, you can set it to 1. And if you can set it to 1, then you can make exactly the same argument that I made some slides ago, that there's the invariant tensor of SU3, and the determinant of SU3 is 1 of an SU3 matrix. The same thing happened here. You've got the determinant, which you could call, even though there's a Hopf algebra, you can call it 1. And that was the proof of invariance in this case. So there are some things that we haven't fully analyzed in this, so we don't know why this happened, why we were lucky and the quantum determinant had this very nice property. But definitely we showed that if you impose associativity, you get the Hopf algebra. One thing that I might not have emphasized is that Hopf algebras are associative by definition. So when you say we have a Hopf algebra, you mean that it's an associative construction. In this talk, we're going to take a slightly different, but I think fundamentally equivalent approach, but perhaps better for applications, which is to actually not define our Hopf algebras in terms of RTT relations, but in terms of something called a twist. So let me talk about what this twist is. Oh, before that, let me say just back up and say what I think what our goals are in the rest of the talk. So the claim is, that was made back in 2008, that these Lee-Strasser theories have more symmetry than is naively visible. You just have to think in a Hopf algebra setting instead of just a Lie algebra setting. Now, is this useful? Is it just a random observation, or can you actually get some mileage out of it? So that's what we want to do. Understand how can we work with these symmetries, first of all, and then how can we apply them on the gravity side. And if we can apply it on the gravity side, can it become a solution-generating technique? The problem is, of course, that the gravity side is a purely smooth geometry. There's nothing non-commutative. There's no Hopf algebras on the gravity side. It's just a normal, just a deformation of the sphere. that you're getting. So how does the gravity side know anything about this quantum symmetry that I'm proposing on the Gates theory side? So I'll discuss some of these questions in the following. Yes?
Perhaps you already mentioned, but in case you have a Hopf algebra, it does not necessarily lead to any conservation law or whatever. It's not the usual symmetry, so
I think it should lead to the same kind of. These are just continuous symmetries, like the same way that Lie algebraic symmetries. So they should lead to selection rules and observation of things in the same way. But I don't know per se. It's basically deformations of the usual structures that we.
I vaguely remember the case of lattice Suzy and also that non-commutative gravity business like 10 years ago. And those people were saying that in their case at least, it's not guaranteed that any conservation law follows.
But was it actually Hopf algebras? Because the thing is, from this perspective, there's no real difference between the algebras and Hopf algebras.
Okay,
making something commutative, as in the sense of fuzzy, whatever, that's a very different story.
Okay. But you claim that once you check Hopf algebra structure, then you can use it for.
Yeah, that's the claim. We haven't done that yet, but we're seeing some indication that it can be possible. But you can ask me again if I don't mention that. So, as a first step to actually understanding what is happening here, we focused with Hector on the integrable cases, which we derived as twists of the n=4 structure in a way that I'll explain. And what the main tool we apply is something called the Drinfeld twist. But we actually call it the Hopf twist in contradistinction to another kind of twist that we'll be using. So basically a twist is also an element like the R matrix that lives on 2 copies of the algebra. Or let's say takes 2 copies to 2 copies. It's a map between these copies. And what it does is it changes the coproduct to a twisted coproduct. That's one relation, but another fundamental relation is that it changes, if you start with a given R matrix, which defines a Hopf algebra, you can get another twisted R matrix, which defines a different Hopf algebra. The crucial thing here is, when you apply this thing that looks like a similarity transformation, it's not actually a similarity transformation. I've exchanged the 2 copies of the algebra. That's why I write F21. F21 means that, if it's something, F acts on 2 elements of the algebra, F21 acts in the opposite way. So this is not a normal symmetry transformation. If it was a normal similarity transformation, things would be very trivial. And if you start with a Lie algebra, you'd still get a Lie algebra, for instance. In our case, we start with a Lie algebra because for n=4, if you follow that Hamiltonian that I had there a few slides ago, maybe I can just write it again. If you take this Hamiltonian, apply it to n=4, which basically means many of these things are 0, h bar is going to be 0, q is going to be 1. Then the R matrix that you get is just identity. Identity times identity. It's a 9 by 9 identity matrix. So that's where we start from. So we'll be applying a twist to the 9 by 9 identity matrix. Now, because the R matrix is identity, and if you follow the discussion that, of course, went a bit quickly, that means that the co-product is going to be commutative, and the Lie algebra, the Hopf algebra is just a Lie algebra for this case. But now, once we twist it, then it's not going to be a Lie algebra anymore. We're moving into the domain of non-commutative coproducts and also non-commutative product. Our product is just matrix multiplication, so that's non-commutative. And so then we end up with a Hopf algebra. So for the beta deformation, we have this extra symmetry, but you can still write down. Usually you write this q parameter of the q deformation. You write this e to the I beta, and if beta is real, this is the R matrix. It's very simple. This one obviously satisfies the Yang-Baxter equation, and this is where the dual background was found using TST. But this has also been understood. So this has been studied by Royban and Bizert, and we were inspired quite a bit by their study of this. Of course, their interest was not necessarily our interest. They cared about integrability, and if you care about integrability, actually there's one thing that I have not mentioned. There's this concept of a spectral parameter, which is a complex number that this can depend on, and you have a generalization of the Yang-Baxter equations that I'm talking about. We do not have a spectral parameter in these, and I can explain a bit more the role of the spectral parameter if I'm asked. How do you get this from a twist? Well, you can take the R matrix unity of n=4 and add to this twist, where you can see basically the only difference is that instead of some q's, I have q to the half, or to the minus half. So Q, here there was a Q minus 1 in the matrix, there's a Q to the half in the twist, but it's still diagonal. You can write it in this nice way as an exponential. So this matrix you can write as exponential of this, where the wedge just means H1 direct product H2 minus the other way. So this is a 9 by 9 matrix, or a difference of two 9 by 9 matrices, where these are just Cartan elements. Okay. So it's a very nice diagonal transformation, and the problem is that this is a bit too simple. You cannot really get much mileage out of understanding the quantum group, because all you get is phases. So many people also in the amplitude studies of amplitudes, they showed that if you take an amplitude of n equals 4, just add the appropriate phases in various places, and you get the amplitude for these theorems, the real beta. It's a bit, of course it's nice, but it's a bit too trivial. So instead we looked at a similar deformation, called the double deformation, which is actually unitarily equivalent to real beta. So you can actually now do a similarity transformation and change your superpotential from the superpotential of real beta to this one. You just unitary transform the scalars. However, our point was we are not going to try to take advantage of this fact. So we're not going to do TST on the gravity side when we try to get the background of this. We're going to pretend that there is no such thing, and hoping that somehow we're closer to the generic case by doing this. And you can see already that the R matrix is a bit more complicated than the real beta one, but still, obviously, it satisfies the Yang-Baxter equation, because these theories are unitary equivalent, and you can write in a more compact form in terms of some kind of shift matrices, and you can write down the twist, and so this is the twist that actually gives you that R matrix, and there's also the inverse twist, and now comes the interesting part. We have this twist. How do you use it to define a new product on your theory? And what I want to do, of course, I have my coproduct and my Hopf algebra, right? That's there, and I can define it using the twist. That's not what I really care about. What I care about is what is the product on my representation space, which is actually the scalars that this SU3 acts on. Right? I'm deforming my SU3. Deforming that SU3 symmetry implies that I have to deform the product between my scalar fields. My scalar fields are what I call here x and y. It's the module, it's the representation space of what used to be SU3, and now is this Hopf algebra. Remember, you can put these scalar fields in a column, x, y, z, and SU3 acts on them. So now I'm talking about what it acts on. Consistency implies that, if you want the Hopf algebra to still act on these scalar fields, well, of course, maybe a better way of thinking about them is the coordinates of the transfer space. So if you were to put a D-brane, these three scalar fields are actually the XYZ coordinates of the transfer C3. So if you want to act as a derivation, that implies that if you deform the algebra product by having now a non-trivial coproduct, you should also deform the modular product. And the way that works is that the new modular product should be defined as the inverse twist times acting on your product of two scalars. So now I know how to, in a way, multiply two scalars in a way that's compatible. But actually, there are two different ways to do this. One is to use f here in the transformation, f minus 1. There's also, you can also think of using f here, and not f minus 1. They're both good for different reasons, but I'm going to focus on this one because this star product does something really nice. And by the way, any formula that I write in a slightly abstract form, you can also rewrite in indices. So here, you can think of x, y, and z as elements of zi. I goes from 1 to 3. So you can, instead of writing this perhaps a bit abstract formula, you can rewrite it like this. Okay? And this is now something that everybody knows what to do with. You just have to sum over the KLs, and that's the action of the star product.
So Costas, you have two different products possible on your module. Is the physics of them different?
Yes, well, okay, the correct one is the f minus 1 that happened previously. That's the one that's compatible with the quadrants product. It turns out, okay, this is just the opposite. And okay, so let me just say this and I'll say what they do. So definitely they're not equivalent. They're not the same, but we're just trying to understand which one is most relevant for the gravity side. So if you want to just consistently define the product on the module, you should not be defining this one. But this one is obviously very related in the following way. Suppose I take this particular combination of scalar fields. There are 6 of them, 6 products, which basically are all the combinations of phi 1, 2, 3, you cyclically symmetrize, so you get these two, minus phi 1, 3, 2, and then you cyclically symmetrize that. Suppose you have that, and now you put a star product, this particular star product, which, okay, perhaps looks a bit like a Hodge star, but I don't want you to think of Hodge stars here. What you get is the superpotential of, okay, and now you get this expression. Now take the trace. Now take this and put it in a gauge theory trace. What you get is the n equals 4 superpotential, but with stars. And if you take the trace of this, you get the superpotential of the doubly deformed theory. Okay. So this is the crucial property that we're trying to get some understanding of, that if you use this particular product, star product, you can take a given expression in the n equals 4 theory, add star products, and you get a deformed star product. Now, if you had the inverse one, it would actually be the opposite. You would take this expression, you would add the star product here, and you'd get n equals 4. So I'm just using it in the inverse way right now. But that would be, so basically, what that is telling you is that the invariant expression, like in the same way that the n equals 4 square potential is invariant under SU3, that would tell you that this expression with stars here would be invariant under the Hopf algebra. So that's the correct thing. But as a solution generative technique, we find it more useful to do the opposite thing. Start from n equals 4, and add the star product and get something which is the new theory that we want to understand. Okay, so another thing you can do just to check this is to expand this to first order. And now, if you do that, so basically expand this and write down the star product that we had before, which was up here, this thing, expand this to first order. What you find is that the difference, so the commutator, the star commutator is some theta. So this brings us in contact with the literature on non-commutative geometry, or non-commutative field theory. But however, this theta is not a constant. This actually depends on the fields. And that's something that Manuela Colaxisi has worked on in the past, and our expressions match the ones she has looked at. Her approach is very different. She was starting from Seiberg-Witten theory for non-commutativity, and using these to get the new backgrounds of the cases he was interested in. If we apply her results to the doubly deformation, we have a perfect match. Okay, so now this is where I want to say a few things about new stuff. So because this was already in the paper, but recently we actually found out that we can write down the general twist that produces the full Lie Strasser theory. The way it works is actually really, I mean, it's a bit complicated. So this is how it looks roughly with these A's, A to F, that depend here are complicated functions of our deformation parameters. But it satisfies all the requirements of a twist, which I haven't emphasized, but they're all there. Apart from one, which is the co-cycle condition. That one ended up being important for having what we call a quasi-triangular structure, which led to the Baxter equation. So it doesn't satisfy that. Okay, and this is how it looks in more detail. So if you, instead of having this I put these to show which are the different elements, but they actually can be related to each other, and Hector has figured out the relations. So you can actually write everything in terms of just 5 combinations of the H's and the Q's, and that's how it looks. So that's the general twist, which gives it the general QH R matrix. And now you can ask, okay, can we redo the same stuff we did before and write down a twist? So a star product that using this this twist, and you can, but now you have to be a bit careful, because one thing that I skipped in the previous slide was that actually, when you apply, if you take a star product, then you apply another star product, you can work out what that means, and what it actually ends up giving you is one of the sides, say the left-hand side of the Baxter equation, acting on it. So you actually get 3 copies of the twist applied to a triple product now, because now you're asking for a cubic relation. If you place the parentheses the other way, you get another combination. Now, are these things necessarily equal? The answer is no. And we can rewrite again this in terms of, it's easier sometimes to write in terms of z's with indices. Here there's no indices, just x, y, z. Here these are elements of a column. And we can easily check that this is not the case. And that's perfectly fine. We don't expect this to be associative, because associativity was actually requires the Yang-Baxter equation. Here we don't have associativity, and for a general twist, of course, if we go to the double deformation that we were talking about before, this is equal to that, and everything's fine. Here, this is not, but something quite miraculous happens. If you take this and you cyclically order, so see here I'm cyclically ordering, but I'm leaving the parentheses on the second two. Here I'm cyclically ordering the same expression, but the parentheses on the first two. It turns out, if you expand this and write everything out, you get exactly the same thing. I do not know the reason for this. It's kind of miraculous at this stage, but it's at the same level, and I think it's very related to the miracle that happened when we were looking back in 2008 at this quantum determinant, which turned out to be an invariant. Even though we had no justification for it because we were applying these RTT relations in the regime where they should not really be applied because the Yang-Baxter equation was not satisfied. But still, we found a proper quantum determinant even in those cases. So there was some hidden associativity there, even though the whole thing should not be associative. Here we also find some hidden associativity in these expressions. Now, if I define the star product using the full twist and write it in this expression here, so you notice it's important the ordering. First I symmetrize, then I put the star product, and then I take the trace. Okay? So the ordering in which to do these operations actually matters. But it's perfectly consistent. All you have to say is that, you know, similar to when you go from classical to quantum, and you ask what is the original ordering that I should have in order to get a particular quantum, like a normal ordered result. It's the same thing here. First you have to normal order your classical superpotential by symmetrizing it, and then you add the star product, okay, and then you deform. So it turns out if I do this, then I get exactly the full general, no approximations, no relation with the parameters, superpotential of the least Strasser theorem. So if I were to take the trace here, I would get exactly the least Strasser superpotential. There's some parameter A which is known, some combination of pHs. So you need to rescale a bit. You can call that kappa. There was a factor kappa in the video. Okay, so that's what we are currently working on. But and it turns out that perhaps the best structure to discuss this story is the category of quasi-Hopf algebras. So we're not going to be in Hopf algebras in the general case, but could it be that we're working with this quasi-Hopf algebra? And these are kind of deformations of Hopf algebras, which are not associative, but the non-associativity is under complete control. Okay? So they're not the most general non-associative thing you can imagine. You have non-associativity, but in mathematical terms, there is an element phi called the co-associator, which actually is an element between 3 copies of the algebra. So it has 6 indices. It acts on 3 copies and gives you 3 copies. And if you want to have two ways of doing the coproduct here, the 2 possible ways, which will correspond to the 2 different placements of parentheses, these are related by the co-associator. This co-associator should satisfy something called the quasi-Hopf Yang-Baxter equation, where you can see it's the usual Yang-Baxter equation, but with these phis inserted. And you can define this through the twist. So if you know an original co-associator, and for our case, this is just identity times identity, because we're starting from n equals 4. In this case, you can twist it and get a twisted one, and we did that, and we found indeed this equation is satisfied. So we have strong evidence that actually the structure we're dealing with is that of a quasi-Hopf algebra, which we get by twisting the n equals 4 Lie algebraic structure in a generic way. And but we need to do a few more checks before we finally finalize this story, because there are some pentagon identities and some other things that actually need to hold to really say this is a quasi-Hopf story. Okay, any questions so far about? Because I'm going to change track a little bit now. Okay, so far what we've done is understand how we can obtain this Hopf algebra and perhaps quasi-Hopf algebra structure using a twist. And it defines an all-order star product, which we use to get deformed superpotential. We can get known results to expand the first order. Okay, now comes the question of the gravity side. Does the gravity side know any of all this algebraic stuff that I discussed on the gauge theory side? So, yes?
Sorry, yeah. So, after you deform the theory, you get a non-integrable theory.
Yeah.
Now, why would that be interesting? But I thought the physical, so the physically, so the physical theories that we want should be integrable. That was mentioned.
Well, I think that's the perspective we're taking. That actually, there's many layers of simplification of our theory, and integrable is perhaps the simplest of all, even though the structures there might be difficult to work with, because you can know everything about the theory, right? In principle, but that's not very realistic. We want to start moving in a direction where we keep as much of the structure as possible, but still, we move away from integrability. That doesn't mean that you cannot know some things about your theory. You cannot probably know everything. You don't expect to know the full spectrum. You don't expect to know all the correlation functions. But we might still be able to, for instance, construct a dual background, okay, which will be very, very useful because then you know something about the strong coupling behavior of your theory. So the question is, are these symmetries strong enough to help to construct a dual background? So I'm thinking of, when you do ADS, say condensed matter, right? I mean, these are not integrable theories in general, but the fact that you might have an ADS dual will help you understand some of the strong coupling physics of the theory. So that's the perspective, okay? So I'm trying to move beyond integrability, but not in one go. Like, we move slowly by deforming the structure, but still having good control of the algebraic structure of the theory, which I'm claiming having this Hopf algebraic structure is not necessarily the same as having integrability. Okay? So there's an extra specification called quasi-triangular, that if you have that, which means Yang-Baxter, then you have integrability. So the best framework that we found to discuss this is the generalized geometry framework. And since it's kind of late in the talk and I don't want to introduce a huge amount of new formalism, I'll just very quickly say what happens. So it's a framework that tries to combine the metric and the B field in one structure that you can deal with uniformly, which makes perfect sense from a string theory perspective, because both the B field and the metric are excitations of the string, of the same string. And the way that Hitchen introduced this method is to consider structures on the tangent plus the cotangent space of the theory, which effectively makes your 6-dimensional transverse space, because remember, I'm always talking about having some D3 branes, in some 10-dimensional space, but now we can describe this 6-dimensional transverse space as a 12-dimensional space, because what we talk about is its tangent plus its cotangent space. So we have these 12 dimensions now, and you can write a basis for it, obviously. So these are the contractions. So this you can think of as vectors, like d over dz, d over dz1, d over dz1 bar, and the forms. So you have a 12-dimensional basis. And the interesting thing about generalized geometry, okay, these are the usual holomorphic and Kähler forms of flat space. Okay, so that's the holomorphic form if you think of flat space as C3, because it's a complex space. And the Kähler form, the interesting thing here is that you define some new objects, which are called pure spinors, which are not really spinors at all. They have some original relation the way they're constructed, but they're just forms. But the interesting and new thing is that you generalize the space of forms to the space of polyforms. Okay, so these are forms where you can add a 0 form plus a 2 form, or a 1,1 form, plus a 2,2 form, plus a 3,3 form. And it makes sense to add these objects that we're not, in normal differential geometry, we would never add, because of course we don't know how to act on such an object, but this is all perfectly consistent in the framework of generalized geometry. So that's one of the new elements here. And the nice thing about this formalism, it allows you to very succinctly describe string theory backgrounds or supergravity backgrounds. For instance, if you want type 2b and you want to have n equals 2, then what you need to find these pure spinors, which kind of generalize. So this is flat space, but suppose I give you some more general pure spinors that describe some manifold. If these are closed, they satisfy a set of compatibility conditions, where, okay, I'm not going to, x is some element of what I had before, so x is any of these here. So if the action of x and phi plus with a particular pairing with phi minus gives you 0, and if they have the same norm, again, I'm using something called the Mukai pairing here, which is defined here. It's just something you can always define when you have forms. If they satisfy these conditions, then you know you have an n equals 2 background in type 2. And if you want to have an n equals 1 background, things are slightly more complicated. There are some right-hand sides here, and so on. But all these have been developed by some of the people The way this works is you define something called a generalized complex structure, and from that you can define something known as the generalized metric, which is a 12 by 12 metric, but which contains inside it the actual metric of your spacetime. This is the actual now physical, 6-dimensional metric of your internal space, and the B field. And you can also read off the dilaton. And the reason this is all there is because I'm working in a purely an SNS, so there's no Ramond-Ramond fields. In this case, because this is just a special, it's an example I chose. For instance, for flat space, there's no B field, so this generalized metric just looks like this. This is just the metric of flat space in complex notation. So, well, what we thought we could do now that we have this star product on the gauge theory side is let's take these pure spinners and twist them. Just take blindly the same star product. Actually, it's not exactly the same. We expanded to first order first. So these are the theta matrices that appeared at some point. So expand this to the first order and act on this on the wedge product. So the wedge product is anti-commutative. We make it non-anti-commutative by introducing this star. And what you see happens, and this is the way we introduce the star, these are contractions. So you see that if these act on a 2 form, what you're going to get is a 0 form, because they eat up one differential each. So now you can take this, which actually turns out to be equivalent to something that Halmagyi and Tomasiello had done maybe some 10 years ago, which is called a bivector deformation. And we were very inspired by what they did. But we want to take it further than them because they had only looked at the beta, the real beta deformation. So if you now take the pure spinners that we have, a flat space, and put the star product there, so you see everywhere here, this used to be just dz times dz bar, now I'm putting a star. And now define the star using the twist, depending on the case you care about. For instance, the double deformation, that's what we actually did in that paper. We plugged in the doubly deformed star product, and we got these more complicated pure spinners. And it turns out that these are compatible, they're closed, so this defines a new n equals 2 background. This new n equals 2 background turns out to be what is known as the n equals 2 Lunémar-Lacena precursor background. What is this? It's a deformation of 10-dimensional flat space where if you were to put D3 branes and take the near horizon limit, then you would get ADS5 cross Lunémar-Lacena. So this is one step before the ADS-CFT. This is at the stage where you just have a flat space, a totally rich flat solution, and then you deform the C3, then you add D branes, and you take the near horizon limit, and you get the Lunémar-Lacena ADS5 cross something solution. Okay. So it's a two-step process, and that's the idea that we followed. We found that we have this now, and if you add D3 branes at the origin of this space. Now, the nice thing about this space, of course, it's not obvious from this, but you have to work through and write down the metric of the space. It turns out to be a cone over a 5-dimensional space. So the usual ADS-CFT story works. You put your D branes at the base of the cone, and one of the directions, the radial direction, just flips over to the other side, and it becomes the ADS5 direction. Okay. So the same story works. So basically, we found this background. I'm going to just flash how it looks. It's not a very simple background. The dilaton looks like this. E to the 2 phi has this thing where these are sine of some angles, alpha and theta. And there's also some complicated combinations, which are called C1, C2, and C3, of the other 3 angles. We're talking about, it's a deformation of the sphere, so there's 5 angles. Phi 1, phi 2, phi 3, alpha and theta. The phi 1, phi 2, and so on are hidden in here, in the C1, C2, C3. It's complicated. But you can find the full details in the paper in case you're interested. But just to see all the components of the metric, they're actually all more or less different, and it's quite a lot of them. And these are the components of the B field, and the Ramond-Ramond fields, because this has Ramond-Ramond fields. Remember, we started with a background which is purely an SNS, but the moment you add D branes and you take the near horizon limit, that it produces for you Ramond-Ramond. We calculated them, but they are hidden in our notebooks. They're too complicated. We didn't really try to simplify them so that one can write them on a page, but we have them analytically, and you can just check that this is a solution of type 2B supercurrent. So this solution is diffeomorphic to the Lunémar-Lacena background, which makes sense because we started off from the W deformation, which was also unitary equivalent to the real beta. So we don't expect this to be a totally new background, even though it's way more complicated. And indeed, you can do a diffeomorphism that you can find it with some work that takes you from one to the other. You would not have guessed it probably without knowing the link from the gauge theory side. But what you get is, okay, so this is just to show that, okay, this is not an embedding of this manifold in 3D or anything. This is just plotting the scalar curvature as a function of some of the angles. So here I chose two angles, alpha and theta, and I'm just plotting to show that this is not a sphere. The scalar curvature depends on the angle that you're looking at, and and of course, depending on the parameter, W, which is the deformation parameter, if this W were to be 0, then this should be just a normal sphere. So the scalar curvature would be independent of the angle you're looking at it. But if you deform W, then you can get increasingly weird sort of shapes here. Okay, so that's what we did. To summarize, we claim that we are somehow we found out how to use this quantum symmetry, which is a symmetry we claim of the classical Lagrangian of these Lie-Strasser theories. And in a simple case, the case where the theory is integrable, which we call the W deformation, which I write here, which is kind of equivalent to this one, but more complicated in practice. We found the star product, and we showed how we can use that star product on the gravity side. And even though, of course, you might say, well, but you're doing something which is quantum on the gravity side, but actually, because of the properties of these forms, we're applying it to forms, and it's a finite number of steps you have to take because they are anti-commuting, so there's not a lot you can do. So this expansion in the star product actually ends, and then we showed that we get a normal commutative n equals 1. Of course, the next step here would be to understand this. Can you say something about the isometries of this new background in terms of this quantum algebra? That's probably the direction of these questions about, are there any, what are the consequences of this quantum symmetry on the gravity side? We don't really know yet, apart from that you can do it. Okay, so the outlook, well, we're trying to fully understand at the moment this quasi-Hopf structure from the gauge theory side, and I expect something to come out on that pretty soon. And we're also with Manuela trying to understand how this can be used to construct the more general or the most general dual backgrounds. So not the integrable ones, but the more general ones. There are some obstacles to this, which I've kind of maybe not really gone into. So our simple approach of taking the star product and expanding to first order and then acting on the pure spinors doesn't work in the more general cases. So you have to find a way to use the full star product, the all-order star product, because you get terms that are there that are not there in the W deform theory. So there are some details, but we're very hopeful that we'll manage with this approach to crack this long-standing problem of finding the dual of these more general n equals 1 theories. And we definitely plan to use some of the work that has been done in Paris, and also Daniel Waldram and so on have been working on something called exceptional generalized geometry, which seems to be perhaps the best language to describe these kinds of deformations. And we're also trying to see if similar structures, this is also with Randall, my student, who's in the back, whether similar structures might arise for n equals 2 theories. So one thing you can do, for instance, is take n equals 4 theory and orbifold it, and so to get some theory with gauge group SU_n times SUN, as Randall discussed in the Gong show. And now you can start, so after you orbifold it, you can start deforming the gauge couplings. And that's supposed to lead to a superconformal, but non-integrable theory. At least that's what the literature claims. So it could be that we similarly to here have some kind of quasi-Hopf structure, even though it's not so clear which is the algebra that's being deformed. It's definitely not some SU3. So we're working on that, and also one can discuss if this is related to any of the other solution generating techniques that have been quite popular recently. For instance, the classical Baxter equation methods or the lambda deformations. Like, are any of these approaches somehow similar to? These are approaches that start from the sigma model side, so it's from the string sigma model. We start from the gauge theory side, So we want to have a consistent gauge theory and then deform it in a way that we think is consistent and then see what happens with the gravity. Here, this is more about deforming the Zoubos model while preserving the gravity of that Zoubos model. So it's not, they're not directly related, but hopefully there will be some overlap. And you can ask questions about higher loops and non-planar effects to this, because we haven't really touched any of that. And the final thing I want to leave you with is, well, we all know that in 2D CFT, there's a very strong relation between quantum groups and CFT, and the fact that the structures of many things, the fusion rules, whatever, depend on these quantum symmetries. If this holds, and you can get many examples, could it be that there is some relation between these new kind of quantum symmetries and perturbably finite theories? Okay, and we don't. I'm just leaving it here. I don't have much evidence that these symmetries are there beyond this simple class of examples that I've been looking at, but it would be definitely worth studying more in the future. Okay, thanks for your attention.
Any further questions for Costas? Okay, then let's thank Costas again.
I know that we thanked everybody yesterday, but let me also take this chance to again thank the organizers and Robert in particular for setting this thing up and bringing us here and contributing this very enjoyable workshop. So thanks a lot.